Hey everybody, today we're going to go over a hydrostatics problem. Um, so in this particular problem, what we're trying to solve is you have a wall over here, and you have this gate that is this like L-beam type thing that is held in place with this point there. So at some height of h, this beam is going to turn. So this is another one that we're going to try to solve symbolically. So in this case, the things that matter for us are the height, this total height of the water, which we're trying to find. It depends on L, which we know from, it's a given information. Z is also given. And then we'll be given a width and density and a G value. So this is what we know. We know rho, we know the width into the board, we know L, we know Z. Let's see, do we need to know anything else? And we know what gravity is if we need it. Okay, so the first thing we're going to do is we're going to set up a kind of a statics problem. So if we look at this portion here, we know that the pressure in a liquid is defined by this here, rho gh, correct? In this case, this part is all at the same depth, right? So we have the same depth from the top of the water, which means that there's going to be a constant pressure at this location. So we're trying to turn this pressure and figure out what the force is. It would be pressure times area, right? Which means that we would get this force, I'm going to call it L because it's on the left side of this thing, would equal the rho g. In this case, when we look at the depth of the water, we're not looking at Z or H specifically, but we're trying to figure out the difference in between them. And then we need to multiply that by the length and then by the width. So this is the force of the left side. So then if we're trying to make this into like a moment equation, we know that our resultant force so our resultant force is applied right in the middle, which this is the resultant force we just calculated, which is L over 2 away from the fulcrum point that we're trying to do the sum of moments about. Okay, so that's our first. So this is force L, and then this is RL, and that equals the moment caused by the left side. And then if we do the same thing up here, except we notice that this time depth is changing. So as depth is changing, we're getting kind of like a directly proportional change in the pressure, where the pressure at the very top of this is 0. Pressure at this very bottom part is this rho g h minus z. So when we do that one, we're going to find that the force portion is dictated by, so force on the right. So you would have your 1/2 rho g H minus Z. And the reason that is because, again, you have the pressure here, but you're essentially trying to find this area under here, which would just be, you know, that would just be the 1/2 rho G H minus Z. Then you need to multiply that by the height and the width. And then, so this would be our FR. And then our R, again, because we're trying to find the overall force, or like the applied force, we know that it's applied at the centroid of this distribution, which is 1/3 from the fulcrum. So that'd be 1/3 times H minus Z. So then when you multiply them together, so you have FR times R would equal the moment caused by that right portion, which would equal 1/2 times 1/3 times rho G H minus Z cubed times W. Let's see, 1/2, 1/3. Yeah. So then ultimately what we're trying to find is we're trying to find out what height is the moment about 0, or this fulcrum point, equal to 0, which equals mr minus ml. So then mr has to equal ml. So our mr again is 1/2 times 1/3 times rho G H minus Z cubed. And that's going to equal our ml, which we said was 1/2 times rho G H minus Z omega L squared. So as we can kind of see here, the 1/2s can cancel out, the rho's cancel out, the G's cancel out, one of these cancel out, so now there's only a squared there, and the width cancels out. So overall, what you're left with is 1/3 H minus Z squared, which is equal to L squared. So then you would have H minus Z is equal to rad 3L. So then H is equal to rad 3L plus Z. And then that will be how we determine what the height needed to turn this gate would be. Yeah, so just kind of some takeaways from this problem is that really hydrostatics is just statics. You just need to write your distributed load out and then calculate to figure out where the forces are being applied. Yeah, hopefully this was helpful. Until next time.